Okay, so we are starting. Tell you the flu. This flu is no joke. I believe we're still at 1.1. So we're going to talk about some more about systems of equations. So last time we spoke about representing equations into matrix form. So this was when you can represent a system as AX equals B, where that was your coefficient matrix, this was the solution matrix, and that was the constant matrix, right? So you can write it as one matrix times another matrix that has all your variables here. Variables. And then you can have another matrix here that has all the constants, and the coefficients go here.
Sorry, what concept? What concept stand for?
Continued. Okay. So we had the matrix form. We also had what we call the augmented form. Right? And that was just one big matrix where it had the coefficient matrix on one side. And then it had the constant matrix, the B matrix, on this side. So those were two ways that we can represent systems using matrices. Now we're actually going to make use of this. Actually talking about solving systems using these forms. Okay, so let's actually remind ourselves how to solve regular equations, linear equations, and then I'll actually do it using this form. We'll draw some similarities, and then I'll tell you guys about the general process. So let's actually do this. 3x minus y equals 7. X plus 2y equals 7. Okay, so let's solve this before linear algebra class. So let's pretend for a second we're back in, algebra, college algebra. We're doing the system. What could we do here? What are some things you might have done?
You can multiply the second equation by 3 and negative 3.
Sure, you can do something like multiply the second equation by -3. The goal would be you want the x to have the same value as what it is in the top one, it is in the top one, so that you can kind of subtract them. This is called using the elimination method. It's actually the method that we prefer to use here. You could also have the decide to multiply the first equation by 2, right? So that would give you a -2 here, +2, and -2y here compared to a +2y there, and you could subtract it that way. So I'm actually going to want to get rid of the y, so let's actually do that. This is equation 1 and equation 2. So what I could do is let's multiply the first equation by 2. So here was equation 1, we multiply by 2. So, and here's equation 2. Right? And then what could we do here?
Take out
Right, how would you do that? What would you do? You can add the equations, right? So if this was, say, I call this a new equation 3, what I could have done was I could have taken 2 and added it to 3. And that would give me what? 7x would equal to 21. In which case, I can divide both sides by 7. I can get my x equals 3. And then I can back substitute to find y. Right? And so I can use either equation. I could just bring this other equation down here and just plug in my x equals 3 to there. And so I would have 3 plus 2y equals 7. And so I move that over. That's 2y is equal to 4. which means that my y is going to be equal to 2. And that was my solution to the system. So this means that the solution to this system of equations is x equals 3 and y equals 2. Or we can express it, sometimes it might be convenient to express it as a coordinate. So we can say that this solution is 3, 2. Okay. Now hopefully that wouldn't be strange to anyone. However, we could augment the original system. Right? If we augmented the original system, what would that look like? And here's what we're going to do. This represents that system. Which kind of means anything I could have done, anything we did to this system when we were trying to solve it, we can actually kind of do that with this construction here. There should be some way to equivalently perform these operations on this system, on the matrix. So let's actually try that. So you guys already copied this down, hopefully, so you already know what we did. So here's our system. Let's start it here. 3 minus 1 is 7. 1, 2, 7. Now, one thing, for aesthetic reasons, I'm going to want to be able to solve for the x. I'm going to move it on top because I know this is a coefficient of the x. I'm kind of care about what that guy is going to tell me. So I can just switch those two. And there's nothing wrong with me switching those two. That's like me relabeling the equations, right? So it's like I can have this guy and this guy, and I could label this as equation 1 and that is equation 2. Or if the mood so struck me, I could have labeled that equation 2 and that equation 1 and nothing would change. Right? So I can kind of switch which equation I'm focusing on at the time. But for aesthetic reasons, I put that one up there. Okay. Now what can I do? Well, I know if I want to solve for x, I'd want to be able to eliminate the y, right? Which means that the fact that this here, that has coefficient 2, I don't like that to have coefficient 2. I'd rather that has coefficient 0, so that there's no y in my equation. So now I want to figure out, how can I get this 2 to go away, right? By, of course, doing something that's legal mathematically that I could have done with the original system. Same thing we did before. This coefficient, this minus 1 here, is representing the coefficient of y. What I can do is I can multiply this row, which represents the second equation, by 2. And I would have gotten 6 minus 2 and 14. And now these guys are the same. I can add these rows, and I can put the result back into the top row. Okay? So I can add these guys, I will get 7. Add those guys, I get 0. Add those guys, I get 21. And now, of course, here, clearly here I have 7y. There are 7 x's, there are no y's, and I get the answer is 21. So because I want to solve for the x, what I can do is I can actually divide that first row now by 7. So I can divide this by 7, divide that by 7, divide that by 7. I would end up with 1, 0, and 3. Okay. Now, because I'm dealing with a bunch of numbers here, I don't want to actually get lost, or if I make a mistake, I'd like to be able to track what I'm doing so I can go back and fix things. So what I'm going to do is I'm going to actually also put in labels to say what I did. So I started here, and right here I just switch rows. So I can just label that to say, okay, I put row 2 here, and I put row 1 down here.
We say we transpose.
We didn't transpose.
Transpose.
Transpose means the
right?
first row becomes the first column.
Oh, yeah.
So we changed everything.
Mhm.
And so transposing would mean you took the y coefficient and made it the new x coefficient in the second row. It just wouldn't work. Transposition, we couldn't have done it with the original equations. We can't do it here, right? So I did that. Then what I did here was the row 2 from the previous line. What I did was I multiplied that by 2. And then what I did was I took row 1 from the previous line
Plus.
and I added it to the row 2 from the previous line. Here what I did was I took row 1 from the previous line and I divided by 7. Right? So I can put these little notes here while I'm doing what I'm doing so I can know what I'm doing, because in the event that we're dealing with a lot of numbers here, there's a lot of room for error and we want to really track what we're doing. Okay? Now, one thing you can realize is that this row here represents an equation. It actually tells us what the x value is. Yes?
Do you mean row 2 divided by 7?
No, I took this row and divided by 7.
On the top you said that's row 2.
What?
So
What? It's row 1. Here's row 1, and I divide by 7.
never mind.
Yes?
Why did you divide by 7?
The same reason why if I had 7x equals 21, that's not satisfactory. I want to solve for the x. I want the coefficient of the x to be 1. Yeah?
Since I have a question, since we already swapped the
Yeah.
two equations, and we already have 1, wouldn't it be easier to solve, to get x to 0 first, and then we solve for 1?
To get x to 0, what do you
we
mean?
have 1, 2, 7, and 3, negative 1, 7. Can we just multiply by negative 3, add it to the second equation, and then divide it by, multiply by negative 1, and then we do multiply the second equation by negative 2 to get, and then add it to the
Sure,
first.
what you're describing is if we eliminated the x first.
Yeah. Wouldn't it be?
We could have done that. What would be the difference? We'd still get the same answer, right?
Yeah.
It's a personal preference. I just decide to eliminate the y. Okay? And I'm really writing labels on what I did on the previous matrix in order to get the new matrix. Okay? So just to keep track of what I'm doing. So all my labels are referring to the previous step, what I did on that previous step. Now yeah.
Sorry, Professor. So then that means that is it row 2 or row 1? That's
Where are you
multiplied by
pointing
2.
at? Here? Or
Well,
here?
you have row 2, yes, that one, row
Yes.
2 times 2, wouldn't it be row 1? Or we're doing it based on the
In the
original?
previous step, this is row 2.
Oh, sorry, okay, did you do the switch? Okay.
These labels refer to the previous step.
Okay.
Labels refer to previous step. So this is row 2 from the previous matrix is what I multiplied by 2.
Got it, it's because I saw row 1 next to it, so.
Yeah, that label is for the previous step.
Right.
So the row 1 and row 2 here is actually referring to up here.
Gotcha.
Okay? So far what do we know? Well, notice that this guy actually gives me an equation. From this I could say that 1x plus 0y is equal to 3. In other words, that tells me that x is 3. Yeah.
What if it was 307, like instead of negative 1?
Yeah.
And you couldn't do anything to the y? Because you said first you would.
If this was 307
Yeah.
here, in that case I wouldn't have to do anything because I would just divide by 3 to get my x. I wouldn't need to do anything to get the x. That would already be an equation like this. I wouldn't need to do anything to the y anyway. So I wouldn't worry about it in that case. Okay. Now technically, I could stop here, and I could see that my x is 3. I could write this guy as an equation and plug in x equals 3 and solve for y. But for the purposes of me illustrating a point, let's actually continue this process. And I want to actually do the same thing that I did with the x, I want to do with the y. So in other words, what I want to get is to get a 0 for the x, right? So the x doesn't play a role in my equation. Have a 1 where the y is supposed to be, and get a number here, and that will tell me what the y number is. Okay, so let's actually do that. So what would happen here? How could we do that? Give me some ideas.
Negative 6 times the first row, add it to the second. Negative 6 times the first row.
Couldn't you multiply 3 to the top row? Negative 3, and then add them?
Or you could divide by 6 rows.
Yeah, here, this guy came from what? The 3 minus 1, 7, right?
Yeah.
Let's say I put it back to the 3 minus 1, 7. Let's say I took the previous row 2, and I divided it back by 2 after I got what I wanted from this guy. Right? Why? Because I want to keep the numbers small, because we're doing arithmetic by hand, which we're probably not used to doing that much. Okay. And so now what? Now I can get to multiply this by something even smaller, right? I can multiply row 1 by 3, right?
Negative 3?
It almost doesn't matter. Just then, instead of adding, I can subtract, but sure. I can multiply by 3 or negative 3. And then this would be what? Negative 9. That would be 3 minus 1, 7. And so now what I can do, and so this would be row 1 times negative 3. Here I just recopied row 2. And what I can do now is I can just add these two. So I can take from the previous line, add the first and second rows. That would give me 0, that would give me minus 1, and that would give me what? Minus 2. This guy I can write back. So take the row 1 from the previous step and divide it back by negative 3 to get back this guy. This guy is almost what I want. This tells me what negative y is, but I want positive y, so let's just actually take another step here and just multiply that guy. Take row 2 times negative 1. And so now I have the matrix in this form. One thing you'll notice now is that my first row tells me right away that my x is 3. My second row tells me right away that my y is 2. Yeah?
Do you use Kramer's rule? Wouldn't that be faster?
Well, we're not doing Kramer's rule. I didn't even tell you guys what determinants were yet. So,
Professor,
yeah.
is that why it's called an identity matrix?
One of the reasons why that, so yeah, you're already starting to spot that there's an identity matrix. One of the reasons why it's important is for this particular process, but it's not necessarily why it's called an identity matrix. But yes, knowing that being able to get an identity matrix on the left here is going to be an important thing, if at all possible. Okay. So what I wanted, but because if you could get an identity matrix here, it's easy to just read off the numbers, right? Notice that in the way that this matrix is set up, you don't really have to do anything. You can just look at the matrix and you can know the answer to the system. So another thing I want you guys to actually realize is that what the things I was doing to the system to bring it into this nice form were things that I could have done with equations. I'm multiplying every row represents an equation. So I can do whatever I can do with equations, I can do to the rows. So I can multiply an equation both sides by 2. So I can multiply an entire row by 2, right? I could divide an entire row by 7. I could swap 2 rows. I could take one row and add to the other row, right? Like I could have done that with equations that we were doing. All the manipulations I was doing with the equation I can actually do on the matrices. You can now see that x is 3, y is 2, easy. And note that what we did with the rows was what we could do with equations. Right, so the operations that we could do on equations, we could do it with each rows of our augmented matrix. And by the way, these guys have a name. These operations are called row operations. Okay. So I just defined for you what's called a row operation, right? And these are basically operations that it's okay for us to do with equations, and so we can do them with the rows of a matrix. Okay. And through row operations, I can be given some matrix that represents a system. I can use row operations to maneuver it into a very convenient form where I can just read the answers off. Now, it might seem to you that this seems like way too complicated. Why did I have to do that when we know how to do this we know how to do this from before. We have the solution here. But the reason is, this process, it's going to give us a lot of rich theory out of it. There are things that we're going to be able to talk about systems that we wouldn't have been able to really see if we weren't really looking at things in this form. Because now when we're studying this set of these just rectangular array of numbers, we'll see certain patterns start to pop out. Like he saw that the fact that there was an identity matrix just popping out here, right? That's something that we knew about before. Right? So there are going to be a lot of patterns that we will be able to take advantage of just by looking at these arrays of numbers. But clearly, in order to do this, in order to be able to solve a system using matrices, we have to do what's called row operations. And so let me define the legal ones for you. There are 3 such operations. Okay. So row operations is something we're going to be doing all the time. So I'm going to tell you what it is legal for you to do at any time. Right? So if it's not one of these, you cannot do it if you're looking at a matrix that represents a system. Okay? So for example, you shouldn't be able to transpose. If you know that the matrix you're looking at is representing a system, transposition is not something you'd want to do because it would not qualify as a row operation. 1, this is called a type 1 row operation. And this is basically the operation that says we can switch 2 rows. In an augmented matrix without changing its solution. Okay. So one type of row operation is switching rows. I can swap 2 rows, and that's just me like relabeling the equation that I'm using. That actually doesn't affect the solution to the original set of equations. So that's something that I can always do. If I want to see things in a certain convenient form, and if I have to swap rows to be able to get it into that convenient form, I can do that. That's a row operation, and that's legal. Here's another thing that I can do with systems of equations, and hence I can always do with an augmented matrix that represents such a system. This is called a type 2 operation. And this is multiplying a row by a non-zero constant. Right? course the constant has to be non-zero, because if you have a bunch of equations and you multiply both sides by 0, you lose all your information and all your ability to solve that equation. But you can multiply an equation by any non-zero number on both sides, and it will not change the answer to the set of equations, right? So that is a legal thing for you to do. You can, in any matrix that you know represents a system, you can multiply any row at any time by a non-zero number, and it will not change the solution to the system. So that's a valid row operation. The third operation is the guy that allows us to do this, that allows us to eliminate. This is called a type 3 row operation. This is a type 3 row operation. It's defined in a very particular way because we want to maintain some properties later on that I'll mention. And it'll also maintain certain properties for determinants and things of that sort when we get to determinants. So it's phrased in a very special way, but it's essentially the same thing that allows us to perform elimination. This is replace one row. By itself plus a multiple of another. This is called a type 3 row operation. So this allows us to multiply another row by a number and add it to the previous row, and then use that to replace the row. These operations do not change the solution set of a system. In fact, they will help us to solve the system. Turns out row operations are useful for other reasons, but one of the reasons is we can use them to help us solve a system of equations. There's something I mentioned, should I mention it here or probably mention it in the next section? I should probably mention it after I tell you about the echelon forms, because then it'll be nicer to see it. Like I'll have to do more hand waving at this point. So I think we'll probably end this section here, and then move on to the next section where I can tell you about some nice forms that we want to use. So let's move on to 1.2, which is called Gaussian elimination. Semicolon. Or Gauss-Jordan elimination. I'll tell you the difference between these two. So we ended the last section with the fact that we can actually use elementary row operations. By the way, I should probably label that. Right, these three things that we can do together, they're called elementary row operations. So if you ever hear me mention elementary row operation, it means I'm talking about one of these three things. So there are three elementary row operations. There are three things that we can do on a matrix that if that matrix represents a system of equations, it will not change the system, the solution to the system of equations. This leads us nicely into Gaussian elimination. By the way, this is the process of using row operations to put an augmented matrix in a convenient form. convenient in one sense. In that we can see solutions easily. But it is useful in other senses. And throughout the semester, you'll see lots of uses for elementary row operations and these forms that I'm talking about. So now I want to actually tell you about these convenient forms. There are two such forms. One is called the row echelon form. Two is called the reduced row echelon form. So given a system, we can write it in matrix form, and we can put it in an augmented matrix. We can use row operations to get it in a convenient form. Convenient in many ways, but one way in particular is that it will allow us to actually find solutions to systems by just reading off the matrix. And there are two such forms that are going to be very nice here, and they each have their own moment to shine, depending on what our goal is in terms of solving the system, or maybe even something a little deeper. So these two forms are called row echelon form and reduced row echelon form. I will now describe each of these forms to you, because you will need to be able to put a matrix into either of these forms upon request. Usually reduced row echelon form, because it turns out that row echelon form is not a unique form, but your reduced row echelon form is a unique form. So if, for example, I'm giving you a question on a test, I'd ask you to go to reduced row echelon form because everyone's answer would look the same, as opposed to there's an infinite number of possibilities here. And so the solutions I write on the board might, online might just not be good enough. Yeah?
Like an antiderivative? Like would be a set of...
No, it's not really the same as an antiderivative. It depends on the row operations you use to get to that form.
Oh.
It'll just, the numbers might look different. Okay? Because it turns out, because the rows represent equations, the fact that if you have, x plus y equals 1, to you that's essentially the same equation as 2x plus 2y equals 2. They're kind of giving you the same information even though they look different. That's where this guy kind of comes in. It gives you exactly the same information as this guy, but it's not in a super lean form, so the numbers can look different even though they're really giving you the same information. Whereas when you get to the reduced, that means you really lean everyone down, you take out all your common factors, everything is just boom, bare bones, everyone would look the same at that point. Okay? So, but they're both very convenient in their own right. Sometimes seeing 2x equals 4 is good enough for you, so instead of getting it to x equals 2, that'll be fine. So let's actually talk about these forms, what they look like. Let's talk about row echelon form. And once I describe these guys to you, it's going to be very easy to make certain conclusions about systems of equations. For example, there's a theorem that says for a system of linear equations, there are only 3 possibilities for the solution. You'll either have no solution, one solution, or infinitely many solutions. By doing this form, you'll see clearly why that has to be the case. There was no other option. Right? And you can see that easily by looking at these forms. It's one of the reasons why they're convenient. There are many other reasons. Okay. So here's how you know that a matrix is in reduced row echelon, is in row echelon. So there's a criteria, there's a checklist that you go through, and you just want to make sure that whatever matrix you're looking at, it obeys this checklist. 1. Any row of zeros is at the bottom. So move any 0 rows to the bottom of the matrix. 2. The first non-zero number in any row must be a 1, right? That's kind of like me saying, I want to be able to say 1x equals blah, right? So I want it to have the form where the first non-zero number in a row is going to represent the variable in that row that I want to solve for. I want it to be a 1. This is called a leading 1. Or we might call it a pivot. I could call it either of those, but that's what that number is. So if I mention, oh, the leading 1 in the 3rd row, you know what I'm talking about is the first non-zero number in that row. So the first non-zero number in any row should be a 1, which we will call a leading 1 or a pivot. Here's the third thing. Except for the pivot in the top row, all pivots must occur to the right of any pivots above them. So I want my pivots to cascade kind of going in this direction, right? So if I have 3 rows, my pivot in row 2 has to be to the right of the pivot in row 1, for example. Right? If I have pivot in both rows, the pivot in row 2 must be to the right of the pivot in row 1. It doesn't have to be immediately to the right, but it must be to the right. Four. All pivots must have zeros below them. In their column. And any augmented matrix that follows this checklist is said to be in row echelon form. Those are the 4 things you have to check. If there are rows of zeros, they should all be at the bottom. Move them all down to the bottom. First non-zero number that you see in any row should be a 1. This is called your pivot or your leading 1. Pivots must occur to the right of any pivots above them, and all pivots must have zeros all the way below them. So it's sort of a parenthetical statement, but I'm kind of going to tell you at this point where the title is coming from. The process of using row operations The process of using row operations to get a matrix in this form is called Gaussian elimination. Gauss-Jordan elimination is the process to get it in the form of reduced row echelon, which is what I'm going to tell you now. So here's the second one. This is called reduced row echelon form. A matrix is in reduced row echelon form if one, it's already in row echelon form. So reduced row echelon form is going to take it a step further. It is in row echelon form. With one new criteria, which is the following. All pivots except the uppermost must also have zeros above them. That is, each pivot should be the only non-zero number in its column. So if a pivot appears in some column, it needs to be the only non-zero number in that column. And if you add that criteria on top of row echelon form, you get what's called reduced row echelon form. These are two very important forms, and you need to know what they are and when something is in that form and how to put something in that form.
I have a question.
Yes.
First part of number 2, isn't that the same thing as number 4?
First part of number.
Like that they must have zeros above them, except for the upper one, and this one says, except for the lowest one, all of them must have zeros below.
No, below. This is below and above.
So it's gonna be like 1, 0, 0, and then it's gonna have like
So
0.
let's say there's a column with a pivot, right? So let's say this guy's a pivot. In general, seeing something like that doesn't automatically mean it's not in reduced row echelon form or row echelon form. But in row echelon form, that 1 would also need zeros here. So there are cases in which this would be fine, but something like that is not fine in reduced row echelon form. Your pivot must have zeros both above and below. There are possibilities of having other than 0 above in row echelon form. That's not.
It has to be 2 zeros or any number of zeros above and below.
Literally in the column, the pivot should be the only guy that's not 0. And when you go take it that far, you say you're in reduced row echelon form. Yeah.
Are we talking about like the left side of the augmented matrix or the whole thing? Like before the bar?
No, I'm looking at the matrix as a whole.
Okay.
Yeah. So I'll give you some examples. It doesn't even care about the bar. So looking at the matrix as a whole, these criteria need to be fulfilled. Let me just tell you what Gauss-Jordan elimination is, and then I'll probably give you some examples, and we'll examine them whether or not they're row echelon form or not. The process of using row operations. To get a matrix in this form is called Gauss-Jordan. there's another thing that you can say. The process of using row operations to change the form of a matrix in general is called row reduction. Or elimination. So I might say, oh, just use row reduction. And what I'm saying is using row operations to break the matrix down into a nice form. Or I might just say, oh, just use elimination, and that's what I'm talking about. But when we're talking specifically about getting to one of these two forms, to bring something to row echelon form, you can say you've done Gaussian elimination. To bring something to reduce row echelon form, you say you'd have done Gauss-Jordan elimination. So that's named after two mathematicians as opposed to just one mathematician. You really amp up on the mathematicians to get more power to do more operations. So, I'm not sure how many more examples I'll get through, but let's just make sure we can identify these before I show you guys how to actually get to these forms. So row echelon, by the way, probably should have mentioned this before, but the abbreviation I'm going to use REF. So sometimes I don't want to write down row echelon form all the time, I might write down REF. Reducer echelon form is going to be RREF. Or neither. So let me write down some matrices for you, and basically I want you to identify for me whether they're in row echelon form, reducer echelon form, or neither of these. And of course you should be able to give me reasons why. So here. So determine which one of those forms it's in, or neither, and then you can tell me reasons for your choice. So you should be able to say, why is it only in row echelon form and not reducer echelon form, or why is it neither of these forms? Yes.
Is the last row the values in B or just another variable?
Irrelevant at this point. Just want you to look at these rectangular arrays of numbers and tell me if it's in row echelon form or reduced echelon form. At this point, don't worry about if it represents a system or not, or what the pieces are. What about the first one?
Row echelon form.
That is row echelon form. Right? There are no rows of zero, so the first criteria doesn't even apply. The first non-zero number, if I'm reading, of course, from left to right, the first non-zero number I hit in each row is a 1. And the one that appears in row 2 is to the right of the one that appears in row 1. So all the pivots that occur, except for the guy in the top, is to the right of the pivot that's above them. So that's actually row echelon form. Is it reduced or echelon form?
No.
Why not? Because of that guy. This guy means it's not reduced row echelon form. Because a reduced row echelon form, if that's a pivot, it needs to be the only non-zero number in its column.
If we use row operations, we could turn this into reduced.
You could turn this into a reduced row echelon. Into reduced row echelon form, it'll take you a couple of row operations. You just multiply this by 2 and subtract it. So you could put it in there, but it's currently not there. Okay. So that's actually row echelon form. What about this one? It's also row echelon form. Why is it not reduced row echelon form? Again, because of this 2. So that makes it not reduced row echelon form.
I have a question.
Yes.
If that 2 were a 0 and you had the 3, 4, and 7 afterwards, it would, then what? In that case, what would it be?
It would be reduced row echelon form. Okay, what about this one, the third one? That's reduced row echelon form. It has a row of zeros, it's moved all the way to the bottom. My first non-zero number in each row is a 1. All my 1s appear to the right of the guys that are above them. And whenever such a guy occurs, everyone else in that column is a 0. There are zeros above and below. So this is reduced row echelon form. None of these guys actually matter. Those numbers can be whatever they want here, right? Because all the criteria have been met. It turns out that in terms of solving a system, this is literally the best form to be in. It is the form that will give you the most information. What about this one? It's neither. Why? Because of this guy. That's my first non-zero number in the second row. It's not a 1. If that 2 was a 1, what would it be? It would be reduced or echelon form. Okay. This one. It's reduced or echelon form. This one? It's row echelon. Right? I have a row of zeros at the bottom. First non-zero number in every row is a 1. All the 1s appear to the right of the ones that are above it. So that's row echelon form. It's not reduced row echelon form because of this guy, and this guy. Those have to be zeros in order for it to be reduced row echelon form. But for now, it's in row echelon form. What about this one? Neither. Why? That pivot is not to the right of the pivot above it. So while the first non-zero number in each row is a 1, that guy's in the wrong position. He needs to either be over here or over there. This way? It's neither. Right? Because a 1 for this row of zeros right here should be at the bottom.
Shouldn't we switch it?
What?
Or just as it is?
Sure, but the question isn't can you put these into this form? The question is, as given,
Oh, okay.
is it this, or that?
No, I'm just asking if it's 2 and 3, then it will be reduced.
Yes, in the event that we switch these two, that would be reduced. Yeah.
So in row echelon form, like below the diagonal or the pivots, it's like always gonna be 0. So it's
Yes, below the
like
pivot should always
kind
be
of
0.
triangle. And then if it's reduced, like that column is only, the pivot is only 1 by itself, right? For reduced row echelon form, it's only 1, the number 1 in each column
In each, yes,
that has it.
yes. And in these examples, my pivots here lie on the diagonal, but they don't have to, as long as it's to the right. So I could have had something like 1, 7, 2, 3, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. And that's also reduced row echelon form, right? So the pivot doesn't have to be right beside it, it just needs to be to the right. So it doesn't have to lie directly on the diagonal, but there should be some sort of cascading in that direction.
Professor,
Yes.
if your third column would have your one, let's say, like maybe at the second column, like you see how the second row, the 1 is in your 5th column,
Which matrix are you talking?
the one down here that you use the example of, it has, as long as it's to the right?
Yeah.
Say the third column had the 1 and the second 0
Right here?
at the third column row.
The third row had a 1
Right.
here,
Would that then change,
and this one is still here?
yes?
Well, then it would be neither, because
be
this
neither.
guy's to the left of that guy, so it
Okay, so it
wouldn't be
has to
anything.
be, the next row has to be to the right of the previous.
Yeah, once you're going lower, you need to be to the right of anyone's above. Okay, that's kind of it. Yeah,
If in the bottom left, the 7 was a 0, that would be reduced, right?
if this 7 was a 0?
Yeah.
No, because these would also need to be 0. All the circle numbers would have to be 0 to be reduced. Which, it'll take us more work to get to that point. We'll have to do a bunch of more row operations. So I'd have to do something like multiply this by a 7 and then subtract, and then I'd have to do a bunch of stuff.
Why do we need a 0? What's the rule? I'm sorry. What's the rule to, like, for it to be zeros, the 7, 2, and 7? For it to be reduced.
To be in reduced row echelon form, those guys need to be 0. Now, how you would get them to be 0, you use row operations. But the fact of needing them to be 0 is going to be convenient, yes.
So they all have to be above the 1, right? For the 0.
Like, the pivot needs to be the only non-zero number in this column.
So what about that one over there?
Yeah.
If the other one, like what about to the left? Like 7, 2, and 3.
This one?
No, the bottom one. Yeah. If they were 0, would they be reduced as well?
As written, if it was 0, no. It still wouldn't work because of these two.
Oh no, besides someone down there. Like,
So
just the
if this was
second-
just a 0,
Yeah, yeah, yeah.
this is reduced. If that's a 0, this is reduced row echelon form.
So it's only above the 1, right? Not like anything else after it.
In reduced, I need zeros everywhere else besides that.
Oh, okay. So,
Above, below.
So even there's 7, 2, and 3 doesn't need to be 0. Just
Right, because there are no pivots in these columns. My pivots occur in these two columns. They need to be the only zeros in those columns. Yeah.
We can't add rows, like if we add 2 rows, we can't then put that third equation down on this third row here. Like if we're given if we're given 2 equations in the
Yes.
system, we can't add a third equation to our matrix.
No, we can't do that. And one reason, why would you do that? You know, in practice, if you're given 2 equations and you just make up this third equation, it's going to be redundant for me.
Well, I'm thinking about for the that one right there, the one REF, yeah, in the corner. Like we could, I guess, yeah. If you were to like reduce that to reduced form, then there would be no point in continuing to have the original equation.
No, you just replace the equation.
I have a question.
So being yeah.
This last question. So for the one that says 9 over there, right? Why is it that even though there's a 1 on the last row?
We're still looking here?
Yeah.
Okay. There's a 1 here?
Yeah, it could still repeat, it wouldn't matter. Those numbers don't matter. As long as it just follows the idea that there's 1 for the first number
Yeah,
and then...
because that 1 is not a pivot.
just is it?
So my criteria for pivots don't apply to him.
What if that one was a 0 and the last one?
If that one was a 0, it would not matter.
And the
And
last
if the one was here, it wouldn't matter.
But let's say the one was on the bottom, it would still be the same thing, right?
If there was a 1 down here and this was 0,
Yeah.
it would still be reduced through echelon form. And that 1 would be the pivot. Okay.
So
We'll
that
stop
was-
there.
sorry, if that was like a 9, it wouldn't be reduced.
No.
It counts as a pivot if it's,
It has to be a 1 to be a pivot and the first non-zero number in a row to be a
I
pivot.
mean, it counts as a pivot if it's in the solution size of the augmented matrix. Because that's B, right?
Well, we're not thinking of this as that.
Oh.
Because technically the bar could be here, it could also be over here, you don't know. Right now we don't care. I just want you to recognize, be able to recognize this form when you see it on there.
In general, do we reduce the solutions? Like, do we?
Yeah, the solutions will be a part of the operations that you're doing. So next time I'll tell you guys how, hopefully now you know how to recognize these forms. Next time we'll talk about how to put something in these forms and then some conclusions that we can take from it.
The
Yeah.
next class we have on Thursday, so are you gonna have a quiz or not?
Oh,
Because
So-
Tuesday is a Monday, Friday.
Yeah, so we'll have a quiz on, so we only have class 1 day next week.
Yes.
Right, so we'll have a quiz on that day, on what we do.
And Professor, can you just I
Did you
sent
try
an
something
email
today?
back. Yeah,
Okay,
you
I'll
sent
check
me an
it
email this morning.
We're gonna find